Hello, everyone. In this video, we are going to talk about three conceptual approaches in probability. So what is probability? Probability is a numerical measure of the likelihood that a specific event will occur. The probability that event A will occur is denoted by the symbol P of A. Let's take a look at three axioms of probability. The first axiom states that the probability of an event always lies in the range between 0 to 1. Okay, so that is P of A is in the range of 0 and 1. When P of A is equals to 0, that means event A can never occur. When P of A is equals to 1, that means event A definitely will occur. The second axiom states that if we have a sample space of an experiment and the probability of having the sample space is equals to 1, so P of S is equals to 1 because the sample space includes all possible outcomes. And then the last axiom, suppose we have K events, A1, A2 up to AK, and these K events are mutually exclusive. Then we have the following. The probability of the union of these K events is equal to the summations of the probability of individual events. Okay, so here we have the three axioms of probability. Next, we will move on to the three conceptual approaches to probability. In this video, we will simply talk about the classical probability, the relative frequency concept probability, and subjective probability. Let's move on to classical probability. The definition. Outcomes that have the same probability of occurrence are called equally likely outcome. And the classical probability rule is applied to compute the probabilities of events for an experiment, all of whose outcomes are equally likely. So we have the formula in calculating the classical probability. The probability of event A occurring is equal to the number of outcomes leading to event A divided by the total number of outcomes for the experiment. In terms of the symbol, the probability of A is equal to NA over NS. NA is the number of outcomes corresponds to event A, and NS is the total number of possible outcomes in the sample space. So let's take a look at an example. Find the probability of obtaining an even number in one row of a die. Okay, so we have 6 outcomes. The number 1, 2, 3, 4, 5, and 6. Okay, suppose this die is a fair die. So the probability of getting these 6 outcomes are equally likely. Okay, so we have the sample space, 6 outcomes. Let A be the event that an even number is observed on the die. So A consists of the outcome of having the number 2, 4, and 6. So what is the probability of obtaining event A? Okay, let's take a look at the formula again. Okay, the probability of having event A is equal to the number of outcomes leading to event A divided by the total number of outcomes for the experiment. Okay, so here, the number of outcomes leading to event A is 3. The number 2, 4, and 6. And then the total number of outcomes in the sample space is equal to 6, corresponding to the number 1, 2, 3, 4, 5, and 6. Okay, so upon division, 3 over 6, then we get 0.5. So the probability of obtaining an even number in one row of a die is 0.5. Let's take another example. We rolled 2 dice. What is the probability that the sum of the 2 dice is 8? So altogether, we have 36 possible outcomes. Okay, and here we have this sample space. Okay, 1, 1, 1, 2, 1, 3, up to 6, 6. Okay, so here we define event B to be the event that the sum of the two dice is 8. Let's do the counting. How many outcomes in the sample space corresponds to event B? So altogether, we have the circled outcome, okay, where the two dice, the first dice, we have the number 2, and the second die, we have the number 6. So the total of the number is 8. And then we have the first number is 3, and the second number is 5. So the sum of the two dice is 8 as well. And then more sample points, 4, 4, 5, 3, and 6, 2. Altogether, out of these 36 outcomes, 5 outcomes corresponds to event B. Let's calculate the probability. The probability of B is equals to NB, which is equals to 5, divided by NS, which is equals to 36. Upon calculations, 5 over 36, we get 0.1389. So this is the probability that the sum of the two dice is 8. Next, we move on to the relative frequency concept of probability. Okay, suppose we want to calculate the following probabilities. The probability that an 80-year-old person will live for at least 1 more year. Or the probability that the tossing of an unfair coin that results in a head. These probabilities cannot be computed using the classical probability rule because the various outcomes for the corresponding experiments are not equally likely. So what can we do? Okay, so we will compute the relative frequency as an approximation of probability. It is stated as follows. If an experiment is repeated n times, and an event A is observed f number of times, then according to the relative frequency concept of probability, we have the following formula in computing the probability of event A, which is equals to f over n, where f is the observed frequency corresponds to event A, and n is the number of times we perform the experiment. Let's take a look at an example. Suppose we roll a die 100 times. 72 times it turned up an odd number. And 28 out of the 100 rolls, the result is an even number. So the probability of having an odd number in the next row, based upon our experiment, the 100 rolls of a die. So we have f over n, where f is the number of times we get an odd number. So in this case, f is equals to 72. And n is the number of times we perform the experiment. Here, n is equals to 100. So upon calculations, we get the probability of having an odd number is equals to 72 over 100, which is 0.72. Or we can compute the probability of having an even number in the next row. Okay, so now the value of f is equals to the number of times we get an even number. In this case, f is equals to 28 divided by the total number of rows, n equals to 100. Then we get the probability of having an even number in the next row is equals to 28 over 100, which is equals to 0.28. Let's take a look at another example. Suppose a die is rolled 1,000 times, and we recorded down the frequency of having the number 1, 2, 3, 4, 5, and 6 respectively. So out of this 1,000 rows, the number 1 appears 100 times. And out of this 1,000 rows, 350 rows, we get number 2, etc. And then suppose we want to find in the next row the probability of rolling the number 2, as well as the probability of rolling an even number. So let's take a look at part A, the probability of rolling the number 2. So here the probability of rolling the number 2 is equals to, okay, what is F? F is the frequency that we get the number 2 out of the 1,000 rows. In this case, F is equals to 350 over the total number of times we roll the die. So here N is equals to 1,000. So upon calculations, the probability of rolling the number 2 in the next row is equals to 350 divided by 1,000, which is equal to 0.35. And then in part B, the probability of rolling an even number. So we get F over N, the formula again. So what is the value of F? Okay, here F denotes the frequency of having an even number. Okay, so even number. So we have the number 2 with frequency 350, rolling a number 4 with a frequency of 50, and rolling the number 6 with a frequency of 150. So the total frequency observing an even number is equal to the total frequency of having the number 2, 4, and 6. So F in this case is equals to 350 plus 50 plus 150. And the value of N is still 1,000. So upon calculations, we get the probability of having an even number in the next row is equals to 0.55. Let's take another example. Suppose 10 of the 500 randomly selected cars manufactured at a certain auto factory are found to be defective. Assume that the defective cars are manufactured randomly. What is the probability that the next car manufactured at this auto factory is defective? How do we approach in computing the probability? Here we let N denote the total number of cars in the sample and F be the number of defective cars in the sample. So the probability of that the next car is a defective is equal to F over N. And in this example, F is equal to 10, the number of defective cars in the sample. F is equal to 10. And the total number of cars in the sample N is equal to 500 in this example. So take F equals to 10 and N equals to 500, we can compute the probability that the next car is defective. So here we obtain a probability of 0.02. Okay, remember that this probability is actually the relative frequency of defective cars in 500 cars. When you take more samples, say you select 600 cars or 700 cars, this probability will change. So here, the relative frequency are not probabilities, but approximate probabilities. If the experiment is repeated again and again, this approximate probability of an outcome obtained from the relative frequency will approach the actual probability of that outcome. That is, we increase the value of N. Do more and more experiment. And this is called the law of large numbers. Okay, so that is for the relative frequency concept. And then next, we will move on to the last concept in probability called the subjective probability. Okay, many times we face experiments that neither having equally likely outcomes, nor the experiment can be repeated to generate more data. So in such case, we cannot compute the probabilities of events using the classical probability rule or the relative frequency concept. For example, consider the following probabilities of event. Suppose we want to find the probability that a student who is taking statistics this semester will get a grade of A in the course. Or we want to find the probability that the S&P 500 index will be higher at the end of the next trading day, or the probability that our basketball team will win in the inter-school competition next season. In the above three examples, neither the classical probability rule nor the relative frequency concept of probability can be applied. All these examples belong to experiments that have neither equally likely outcomes nor the potential of being repeated. Okay, so how do we get such probability? Subjective probability is the probability assigned to an event based upon our subjective judgment, experience, information, and belief. Okay, so there's no calculations for subjective probability. Okay, so this is based upon our subjective judgment. Okay, so here in this video, we have talked about the three conceptual approaches in probability. Thank you very much and see you next time.